This portion of your textbook really hopes to establish what is a battery, and it discusses the electrochemical basis behind batteries. To begin with, what is a battery? A battery is anything really that converts chemical energy into electrical energy. And so remember, atoms or even molecules themselves have chemical potential. They have potential to do work. And if they are combined in just the right way, then when they do that work, we can capture that energy as the movement of electrons, which is termed current. And that current is what powers all of our devices, from cameras to cell phones to TVs, anything really. Anything that uses power is going to have electrons moving, and that electron movement can come from either a battery or your wall outlet. Either way, both forms come from chemistry. Alright, so let's look at an alkaline battery, just a simple 1.5 volt alkaline battery. That is also considered what's called a galvanic cell. A galvanic cell is anything that reacts spontaneously. So meaning your battery, if you hook it up to a device and you put the battery in the right way, then electrons are going to move spontaneously. You're going to start powering your device from your battery. If you accidentally put the battery in the wrong way, then that's no longer a spontaneous direction, and you won't get your flashlight to turn on or whatever it is that you're trying to power. So this is showing the basic setup of a battery. So you have a positive terminal in and a negative terminal in. The part that's sticking out is, by convention, that's your positive end. That's considered your cathode. And the way I remember it is cathode has a T in the middle, and the T kind of looks like a plus sign. So that's your positive end. Cathode means reduction, and so that's just by convention. That's just the way we've established it kind of from the beginning of the development of electrochemistry. And so cathode is positive for reduction. Anode is negative for oxidation. And so remember, oxidation is loss of electrons. So if we look at this chemical equation here, what's happening is you have zinc, which typically there's like a zinc paste inside of your battery. When the zinc paste reacts with hydroxide, it's going to produce zinc oxide, water, but then also, more importantly, 2 electrons. And what will happen is your 2 electrons will flow into whatever your thing is that you're trying to power, and then back into this positive terminal. And when that happens, you now have 2 electrons available that can react with manganese oxide. And manganese oxide is at the cathodic end. And so this cathode has manganese oxide that's just waiting patiently for 2 electrons. So whenever it's powering a device, those electrons flow from the zinc to the manganese oxide, making it so now manganese oxide can be turned from manganese 4 oxide to manganese 3 oxide. And when that happens, you've now completed an electrochemical reaction with 2 half-cell reactions, is what this is called. Now what's really neat is within a battery there has to be some kind of partition, and so typically there is some partition, like a piece of paper almost, that is going to be some porous membrane that's going to prevent these two from interacting. Because if zinc could just directly interact with the manganese through the walls of the battery, the electrons would flow this way, but you need them to flow through your device. And so whenever you set up a battery, it's got to have some kind of pore that prevents those ions from moving. And as it's doing that, it's going to have the electrons are going to be forced to make that circuit, and now you've got a nice way of powering devices. What's really cool is the original battery was simply different metals that were separated by cardboard, essentially, that was soaked in salt water. And so just by piling like a zinc and then some paper and then a different metal and then some paper on top of each other, they were able to create very simple batteries. These batteries were huge, but they made batteries that could power lights out of them. And so this is just the basic setup of a battery, but let's give a couple more examples just to make sure we understand. This is a setup that you see a lot in textbooks where we've got a battery that's inside of a beaker. Are real batteries going to be set up like this? No, but this is a convenient way for us to test and see if our battery is going to work, because one of the biggest things that we're trying to figure out in the world is how can we store electricity better, because electricity is often made, even like in a windmill or something, it's made, but then if you can't store it, it just turns into heat and it's lost to the atmosphere. If we could save every bit of energy that's produced, we would have a much greener society. We wouldn't have to rely on, our hydrocarbons, our fuel, our coal, that kind of thing. So a lot of this research in battery production is just how can we make a more efficient storage of these electrons so that way we're not wasting energy. And so this is a beaker setup that is showing you the basic setup of what's happening inside of that battery that we just looked at. So in this case, you've got an overall net reaction where you've got a copper rod and you've got a silver rod, and then there is a porous partition, which is just like that paper I talked about for the battery, separating the two of them. And so in this case, you also have to have a solution, and that solution's whole job is just to provide the metal ions that are required for the reaction. So if we look at this net reaction, we could separate it into two separate reactions, where you've got your copper reacting with copper 2+, and you have your silver reacting with your silver metal. And so if you separate those into half reactions, now you can figure out how many electrons are being transferred. Meaning, going from copper 0 to copper 2+, we lost 2 electrons. That means 2 electrons are written as on the product side. Going from two silver positives to silver 0, each silver lost a charge, okay, or it went down in charge, therefore it gained an electron. And so since there were 2 silver positives, we needed 2 electrons to balance that out, and now we can see that 2 electrons were transferred between the silver requiring them and the copper releasing them. So essentially copper released 2 electrons and gave it to your silver. And that's what we've been talking about this whole time, but now it's applying that to the idea of a battery. And that one reaction will happen at an anode and one reaction will happen at the cathode. And remember, at the anode is your oxidation. And so that's why this copper here is shown over here as the anode. And then your cathode is the positive, and that is your reduction, okay? And that's just because it's getting reduced. That's just all by convention, okay? All right, so this is the basic setup for a battery. Let's go on and let's try and practice how we can create these half reactions, because I think at this point you should be really good at saying, okay, copper was oxidized, silver was reduced. But if you're given just the overall reaction, can you write it as 2 separate half reactions like we've done here, and then see if they all balance out? And so let's practice doing that on this slide. So I am giving you this reaction. Oxygen plus hydrogen yields water, and if you leave oxygen and hydrogen, just let those gases form, naturally they will spontaneously form water. You'll get a little bit of condensation. And we know it doesn't happen the opposite way, because water, the oceans, are not naturally turning into gases, or else we'd all be dead because we wouldn't have any air to breathe. I mean, water to drink, we'd all only have air that and that's not quite enough. Okay, so let's get on with it then. So with this reaction, we could easily see that we need to balance it by putting a 2 in front of my hydrogen and a 2 in front of my water. But that's just normal balancing like we've done before. In order to balance it electrochemically, there's a couple more steps involved. So when we do this, you want to write your half reaction. So just break it apart into one reactant going to a product, the other reactant going to another product. Just try and separate it in a way that kind of makes sense. So in this case, they each have to share the product. There's no other option. Sometimes they'll each get their own product. So meaning like this one, it was obvious to see that copper goes to copper, silver goes to silver. Just kind of separate them. And then what you want to do is you want to balance all of the elements other than oxygen or hydrogen. Since that's all we have, we're going to skip that step. The next step says balance oxygen by adding water. So in our first reaction here, we're going to focus on it first. Oxygen needs to be balanced by adding water. So we have 2 oxygens, and then we only have 1 oxygen in water. So we need to put a 2 in front of the water in order to add a water to that reaction. Then we're supposed to balance the hydrogens in that equation by adding H+. So if we look on the left side of this top equation, there's no hydrogens. If we look on the right, there's 4. So we need a total of 4 H+ added to the left. Then we need to balance out the charge by adding electrons. So in this case, my left side is 4+ and my right side is neutral. So I need to add 4 electrons to the left side to balance out that equation. Then we do the same thing to the second equation. balance out the oxygens by adding water, then balance out the hydrogens by adding H+. So if I notice there's 4 hydrogens on the left, 2 on the right, so I need to add 2 protons to the right. Then balance out the charge by adding electrons. Here's a hint, electrons and protons always go on the same side. And now we're done with this equation. So then we have to look at step 6. Balance the electrons across half reactions by multiplying to find the lowest common multiple. Meaning, I only have 4 electrons in the top and only 2 electrons in the second equation. So I need to have the same number of electrons in both equations. So I'm going to rewrite that second equation, but multiplying it by 2 to give me 4 electrons. Before I get too far though, I'm going to notice there's waters on both sides of my equation, so I can cancel them out. And then I multiply the hydrogen ions, and the electrons by 2 to give me this equation. And then I'm going to bring down that top equation so I can add them together. And then you'll see that my 4 H pluses cancel out, my electrons cancel out, and I'm left with 2H2 plus O2 yields 2H2O. And doing it this way, I was able to figure out what were my 2 half reactions and which were my 2, and what was my final net reaction. Also in this, you should be able to tell which one was oxidized. So remember, oxidation is loss of electrons. Reduction is gain of electrons. So oxygen was reduced, hydrogen was oxidized. Another way of saying that is that hydrogen, since it was oxidized, it is my reducing agent. Oxygen must therefore be my oxidizing agent. Alright, so then let's look at a couple more batteries before we finish out this lecture. So remember, battery's whole job is just to create chemistry that produces electrons. So in this battery example, it's a lead acid battery. So if you notice in that equation down there, it has H plus in it. It's an acid. What's really neat about these batteries is they don't really just run out. You can just keep supplying extra protons and then they will continue to regenerate. So they're rechargeable. These are the types of batteries that you might have in your car. Which is great. They're fantastic in the fact that your alternator is going to recharge, hopefully, your battery as your car is running. I have driven a Volkswagen Beetle before and my alternator not work, and that makes for a long day. But these are bad for the environment. You can't just take your lead acid battery and toss it in the woods. You can, but I don't recommend it. It's very bad for the environment because it has lead in it. But it is rechargeable. Okay, so this battery became very beneficial for whenever we have automotives and we wanted to go from point A to point B without having to stop and put in a new 6-pack of AAA batteries. Okay, so much more improvement. Yay, chemistry. The next kind of battery I want to talk about is just lithium-ion rechargeable batteries. So lithium-ion rechargeables were a huge increase in the battery world. Whenever these came about, we no longer had to just use the same old AAA. We can now recharge the batteries after we have used them. These batteries, instead of having a separator that won't allow the two chemicals to mix, they allow the chemicals to flow between the membrane. It's selective though, meaning whenever there is no load, the electrons flow one way. Whenever there is a load, meaning whenever you're recharging it, you can force them to go the other way. And so there's a really good article here from How Stuff Works. If you want to click on it and read it, it tells you all about the lithium-ion battery. It's just really neat because either the electrons are flowing one way and powering your device, or the electrons are being supplied by the wall and causing the chemicals to reshift to where they originally were. Another battery of interest is fuel cells. A lot of our automobiles are getting shifted over to try and use this proton exchangeable membrane, this PEM, fuel cells for short. And the idea behind this is that we can continually produce energy as long as we are being supplied with our oxidants and our reducing agent. And so often our oxidizing agent in these fuel cells is oxygen and our reducing agent is hydrogen. And what's fantastic about that is you can just pull that from air. And so the idea is if we continually supply oxygen and hydrogen to this membrane, then we're going to constantly have plenty of fuel and we won't have to go to the gas station and refuel. It's a great idea, but there's still a lot of problems. It's not super efficient. It is still a clean way to produce, an efficient way to produce energy, but it's not going to be efficient as like our gasoline is in allowing us to go long distances. And And also with this hydrogen fuel cells, they only emit water. There's not all the problems of what gases are going to be produced, smog, all of that. It's just a very clean way to produce energy. But it's expensive, the performance issues, and then also the durability. How long does these fuel cells last? Those are some key challenges that are going to have to become overcome before you'll start to see these fuel cells used in every commercial vehicle on the road. So with that, there's lots of batteries, but thinking about how a battery works is important, and understanding it can help you figure out maybe the next step of what are the other uses for these batteries? How could we make better batteries? But with that, go read section 8.4 in your textbook, and we'll be ready for the next video.